And now, for something completely different, phase changes. So a gas cannot stay a gas in all physical conditions. So let's write the ideal gas law real quick. Pressure times volume is nkt. N's the number of molecules, presumably a constant. K is Boltzmann's constant, presumably a constant. So you only got three variables: pressure, volume, temperature. Let's pick a couple of them to plot. So let's plot velocity and whoa, professor, hold back. That's not velocity, it's volume, of course. No velocity in this equation except for the kinetic theory of gases that we just did last lecture. Anyway, starting over, let's do volume. So you can imagine compressing a can of gas down and basically cooling it off. So it's sort of equivalent. So cooling off would be toward the left, and shrinking would be down like this. Now, if we if we held pressure constant, volume equals temperature within a constant. So for the ideal gas law, we've got some curve that is pretty easy. It's a straight line. At some point, though, we're going to run into additional physics. So as we cool our substance down and pretend it's something like, I don't know, I'm missing on all the substances I know, maybe it's nitrogen or something. So in this linear region, that's the ideal gas behavior up there. And most gases behave like that to a really high approximation, super successful theory. At some point, though, you're going to turn liquid. So when you cool it off and cool it off, then at some point you're probably going to change phase. So when you go to a gas, from a gas to a liquid, generally speaking, your volume just shrinks a lot. So this just plummets to some new level. And that new level may be fairly stable until it freezes. And then it drops to a new solid phase. And then that will stay all the way to absolute zero. By the way, if you extrapolate this ideal gas curve, you find absolute zero, which on the Celsius scale is minus 273.15. Okay, that's interesting. So we've got liquid and we've got solid. Often, especially in the solid phase, you can have more than one solid. So there are several ways to pack crystals. When something turns solid, all of the molecules arrange themselves into an interlocking crystal structure, and they don't travel, but they do vibrate. So this notion of internal or thermal energy is still true, but it's just vibrations within the lattice. So all the little guys stay put, but they do still quiver, and that becomes our thermal energy. In the liquid phase, they're free to slide around. All the particles are kind of in close contact with one another, so they don't obey this gas criterion, but they do jostle around and spin, and they have more freedom, so that's their thermal energy. And then the gas, when the gas phase kicks in, then it's just mostly the translational motions of those particles, individual particles. That's the kinetic energy. All right, I think I'm digressing. So let's plop up another diagram. Look how fast and accurately I drew that. This one is pressure versus volume. And for one temperature, you can draw a curve. So this happens to be for for water up here. And I've got this one on there because I didn't like the one in the book, because I'll get there in a second. But if you got one temperature, so here's water at about 450 degrees Celsius in this blue trace here, and it comes down, and this is all of this water is steam. So this is all gas up here. That's fine. Call it gas. So all this region is gas, and this is one temperature at different pressures. So as you change pressure, the volume of your gas changes quite a lot. So this is for constant number of particles. So say you had Avogadro's number of particles at very low pressure, you'd expect that to take up a lot of volume, and it does. And then you start compressing it, and by gum, it shrinks. And this is, and you keep applying more and more pressure, and it shrinks more and more and more. And that's kind of an ideal gas thing. You notice there's some bumps and wiggles in this line. If this were really an ideal gas, it should be a really smooth curve with no inflections. So I'm not sure I even managed it, but if that were a smooth curve, that would be a true ideal gas behavior. When you get reality creeping in, you do get a few inflections and bumps and wiggles. Okay, so pressure and volume diagram. Let's take this red one, because this is really important. This is called the critical isotherm. For water, it's 374 degrees Celsius. And that's kind of hot. And so this curve has a quite non-ideal behavior. And right in there, it goes flat. So this is high pressure, and then low, as pressure drops, it comes down like that. And so everything to the right of that curve is gas. And then there's also a line, a dotted line here that's kind of important. So everything above that is gas as well. So we have gas in here, gas in there, gas in here, and in there, in this interstice right there, that's also gas in there. The book calls it vapor instead of gas. In my field, we don't even make that distinction, but maybe it's important sometimes. So between the critical temperature and this line is perhaps important sometimes. Anyway, it's a very important dividing line. You can't have liquid above this flat bit, this critical point. Now in here, that's a crazy interesting place where you're partially gaseous and partially liquid. And so you have to traverse that region in order to make it over here. So in here, that's where liquids live. We're kind of ignoring solids for this diagram. So everything in there is liquid, and if I stipple, I need a color to stipple. So if I stipple the liquid region, it only goes up to that critical temperature up there. And everything in this tiny little wedge down here, that's where the liquids are. Whew. Okay, so we have like coexisting liquids and gas in here. All gas everywhere else. Hopefully some ideal gas behavior up here, but as you approach these phase change areas, you get non-ideal gas behavior. Whew, one more, and that is if we plotted pressure and temperature. So let's try that, very much not to scale. So this is very much a sketch, and it'll be different for different diagrams. But it kind of looks like this. So you have a special point. I'm not even going to label the axes. You kind of have a special point called the triple point, and then you can have different regions like that. So this thing is called the triple point. Point. And then in here is liquid, and in here is solid, and then over here is gas. So at low pressure, this is kind of interesting. At low pressure, so low on here, a lot of substances have this region where at 0 temperature, it's a solid. No surprise there. And then there's a phase change, but it goes directly from solid to gas. So all this stuff over here is gas. So that is interesting. When you go from solid to gas, you call that sublimation. The real world example you might be familiar with is carbon dioxide or dry ice in the solid phase, and then it goes directly to gas at quite a lot less than room temperature. But it doesn't pass through a liquid phase in the process. It just goes from ice to vapor. Fascinating. But at a little higher pressure, you can make liquid CO2. So if you had a pressurized can or something, CO2 goes through a liquid phase on the way as well. And you're familiar with water, which goes from solid to liquid to gas. So that sort of temperature rise thing is okay. This guy here, this is the thing from the last point we called the critical point. That exists on this diagram as well. And so what happens is liquids are capped at that pressure. Above that pressure, liquids and gases behave basically the same way. So we call all those things gas. This thing can still go up, and so there's more gas phase stuff up here. This is still solid in here. So this pressure temperature diagram, often called the phase diagram, and it does illustrate these different phases. Okay, in summary, what have we learned? Well, we've just kind of explored things, haven't we? We've just kind of talked about solids, liquids, and gases, and the boundaries between their layers. If you're gonna go from solid to gas, or solid to liquid, or liquid to gas, there is often an energy cost when you change state, because gases have a lot of thermal energy. They've got a lot of motion, but liquids don't, for example. So when you go from liquid to gas, that process is called boiling. And so when you boil your liquid to become gas, it doesn't happen instantly. You have to inject some energy in that. And a similar thing from liquid to solid. There's an energy kind of boundary between them, and you have to cross that. Or if you're going from liquid to solid, then some heat has to come out before that solid can form. And then there's one here at the sublimation line as well.